Welcome to College Algebra once again. Today we're going to talk about P7. In section P7 we're going to be looking at rational expressions. A simple description for these types of expressions would be fractions with polynomials. This always comes after our study of both polynomials and factoring because a lot of factoring is required to do problems involving these. So if you haven't already done that homework, it would be a very good idea to go and do it. I'm going to have some initial definitions. A fractional expression is pretty much what you would expect it to be. It's just an expression where you have some kind of algebraic expression on the top, some kind of algebraic expression on the bottom. A rational expression is a more specific version of one of these. A rational expression is a fractional expression in which both the numerator and denominator are polynomials. So this one is a rational expression and this one is a rational expression, but this is not, because the square root of 5x minus 2 is not a polynomial. It's a radical. It has a polynomial inside it, but that doesn't count. I mean, to be a polynomial expression, it has a very rigid structure, which we've already gone over. It has to have non-negative integers in the exponents, and it just has to be a collection of monomial. So this is going to be where we get our first set of exercises for the section. We're going to be finding the domain of an algebraic expression. Domain of an algebraic expression is the set of real numbers that the variable is permitted to have. My pet definition is that it is the set of real numbers that you can plug in to the expression and get back real numbers. Because there are lots of different types of expressions. Take a very simple example, 1 over x. I can plug in almost any real number into that and get a real number back, except for 1. If I plug in the number 0 into 1 over x for the variable, it will be undefined. Undefined is not a real number, so 0 would not be in the domain. Similarly, if I looked at square root of x, and I think this will be on the next slide, if I take an even root of a negative number, that's not a real number. We've seen before, square root of negative 4 is not a real number. So the inside of a root has to be non-negative if you're going to get real numbers back. So that leads to these two specific cases you can look for. We'll have other restrictions on domain as the semester goes on. But for right now, we just have the two. If you have a fractional expression, you've got to worry about where the denominator is 0. And if you have a radical expression, you've got to worry about where, for what values of x, would the radical be negative, the inside of the radical be negative. And it only really matters for even roots. Odd roots have no such restriction because you can take odd roots of any real number and get a real number back. This is a table from the book where they give you a few quick expressions and their domains. I'll say in the homework, most often they want you to write these in interval notation. So interval notation for this would be negative infinity to 0, union 0 to infinity. This one would just be square bracket 0 to infinity. And that one, it's different than the square root x because it still has the square root in, so still x has to be greater than or equal 0, but it can't equal 0 because 1 over 0 would be undefined. So this one would be 0 to infinity, like so. Oh, like so. Let's look at some examples from the book. The first example I'll look at will be exercise 11 here. It's a fairly simple case because it's a rational expression. It has no roots in it. So I'm only worried about where the denominator might be 0. I don't even have to really look at the numerator in this case. So I'm just concerned about when x minus 4 equals 0. Well, you can solve that equation if you want. That just gets you x equals 4. That's the only point I have to rule out of the domain. So the domain would be negative infinity to 4 union 4 to infinity. That's interval notation. Set builder's notation, which I don't think you'll be able to plug into the homework. But if I were, say, giving you a test, a paper test, I would certainly accept this. X such that x is not equal 4. And similarly here, just have to consider the denominator. You'd end up with t equals negative 2 would be the problem point. So it would be everything except negative 2. Union negative 2 to infinity. Up here, number 7, you notice there are no roots and no divisions. No rational expressions, I should say. Well, that means none of the issues we've seen will crop up at all. In fact, this is a polynomial, and all polynomials are defined for all real numbers. So that means the domain of this is all real numbers. So I can express that in interval notation as negative infinity to infinity. Usually in set builder's notation, they just cheat and say, like the double barred R. Technically, set builder's notation would be x such that x is a real number. On 15 here, we have a root. So what did we say have to be true about the inside of even roots? They have to be non-negative to be in the domain. Well, we know how to set that up. If you're non-negative, you are greater than or equal 0. You can solve an inequality like this, like a simple equation. Just move the 3 over. X is greater than or equal negative 3. And now we have that is our only boundary, so our domain would be, I need a square bracket, negative 3 to infinity. Down here, these are basically the same problem. I just changed the sign on the bottom, so I'll get a slightly different answer depending upon whether it's a positive or a negative. This is the original version of the problem. The inside of the root still has to be positive, non-negative, so it still has to be greater than or equal 0. It means x is greater than or equal 0. And x cannot equal negative 1. Well, if you look at the number line, so we're starting at 0 and going to the right for x greater than or equal 0, and we can't have negative 1. Well, by default, we can't have negative 1 if we're in this x greater than or equal 0. So x greater than or equal 0 is our only real condition here. So that means interval notation, it will be 0 to infinity. That'll be different over here because in this problem, start at 0, but now 1 is the issue. And 1 is in our set, so we have to rule it out, which means this is going to be broken up into 2 intervals, 0 to 1 and then 1 to infinity. So that would be our interval notation. So square bracket 0 to 1 with a parentheses, union 1 to infinity. And that would be the domain. Just really have to keep those two conditions in mind. Just if you have an even root, you need the inside of the even root to be non-negative. And if you have a rational expression, you need to make sure the denominator is not 0. The rest of what we'll be doing in P7 amounts to what we've always done to fractions. The first thing we're going to learn is how to reduce these new types of fractions. Then we're going to look at multiplying and dividing these new fractions, then adding and subtracting. And a lot of the rules will be basically the same. So we're going to start out with reducing. To simplify a rational expression, you may remember when we did it with numeric fractions, the idea behind it, say if I had 12/20ths. Well, the idea behind how I can factor these is I can pull out a common factor, 4 times 3, 4 times 5, and then I can divide by that common factor. Well, it's going to be the same idea with polynomials. You factor them down completely, and then you reduce away common factors by division. So factoring is a big part. We're going to have to factor all these polynomials, numerator and denominator. So let's take a look. The first problem we're going to look at is exercise 20. Here I've got 14t squared minus t over 7t. Restrain your urge, if you have it, to try and reduce between the 7t and the 14t squared. You cannot do that, any reduction, until we've factored both the numerator and denominator. That's the rule. And one way to see why I can't do that is just looking at numbers. If I had 3 plus 6 over 3, I could not do this. That would get me 7. And 3 plus 6 over 3 is not 7, it's 9 over 3, which is 3. I could do this, though. Pull out a 3 from the top there. I have 3 times 1 plus 2, 3 on the bottom. Reduce away that 3, and then you end up with the correct number. And that's what we're going to be doing here. That's a 1 plus 2. So I'm going to factor the top. All I can really do at the top there is that there is a common t. So I pull out the common t. I have 14t minus 1. Now I have all of that over 7t. So I reduce away the common t. And now I just have 14t minus 1 over 7. That's as far as I can reduce it. 28. I have to work a little harder on the factoring. Both trinomials. So let's see here. The top one I can use the shortcut on. Factoring pairs of 18. Negative 18 would add to be 3, would be 6 and 3, and the 6 would have to be negative. So that would be y minus 6 times y plus 3. On the bottom, I think it's going to be this, but I'll check it. 2y, I think it's going to be plus 3 here, and y plus 1 here. You can check that by multiplying the outers and the inners to make sure you get the middle term, but I'll go ahead and do the full process over here. 2 times 3 gets me 6. I need a factoring pair of 6 that adds to be 5. That is 2 and 3. So I have 2y squared plus 2y plus 3y plus 3. Factor by grouping, pull out a 2y in the first group, y plus 1. Pull out a 3 from the second group. And yeah, that gets me y plus 1 times 2y plus 3. When you have a narrow set of factors like this, I often do trial and error, because there simply aren't that many options. The first terms had to be 2y and y. The last terms had to be 3 and 1. So the only question was, how were they arranged? And you can figure that out pretty quickly, just because the middle term is the multiplication of the outers and the inners. So once you know it has to be 2y plus 3y, then there's only really one combination. But anyway, we factored out the numerator, we factored out the denominator, and we can't do anything. There are no common factors between top and bottom, so that's as far as it's going to go. Let's look at this one. Top is a difference of squares, so I can factor it using that formula. 1 plus x, 1 minus x. Oops. And on the bottom, that is a difference of cubes, so I use that formula. X minus 1, x squared, plus x, plus 1. Now, you might think there doesn't look like there's any common factors there either, but these two, x minus 1 and 1 minus x, are very close. In fact, they are the same factor, but they just have opposite signs. They have the exact same terms, but opposite signs. And I can fix that very easily, because I can just take one of these and factor out a negative 1. So I'll say factor a negative 1 out of the one on the top. So 1 plus x, then I factor a negative 1 out of that one. I'll reorganize the terms so it's the same order. X minus 1. I flipped both signs. Negative x became positive x. Positive 1 became negative 1. And now, that x minus 1 will reduce away, and we'll end up with, I might as well write as, got to multiply that negative 1 through, I guess. So that'll be negative 1 minus x over x squared plus x plus 1. And it'd be fine to write it as negative x minus 1 as well. Doesn't really matter the order, as long as you keep the signs with the proper term. So that is finding the domain of a rational expression and simplifying a rational expression. Next time, we will look at multiplying and dividing rational expressions, and maybe do some addition and subtraction. It depends on how much time we will have. I will talk to you then.